Welcome back to Cradle to Grave Algebra. Today will be a little more exciting. We're going to just derive our own equation by recognizing patterns and generalizing that pattern. So that being said, let's do a little quick refresher on exponents. We're going to start with asking, what is 10 to the first power equal to? I think most people know that the rule is anything raised to the first power, we normally get rid of that little 1 and we just call it whatever the base is, the 10. So like 2 to the third power, we all know by now should be 2 times 2 times 2. So the base, which is 2, multiplied by itself the exponent amount of times, right? So the base is the 2 and the 3 in this example is the exponent. Exponent, right? In that example. All right, so this is equal to 8. 2 times 2 times 2 equals 8. And we've got the general pattern here. So that's what exponents are. I think you understand what those are. Let's jump into that derivation that I'm talking about. So with that derivation, I'm going to start with tens because I think that's an easy number to work with exponents. We're going to say 10 to the 1, and then I'm going to multiply it. I'm going to say multiply that by 10 to the 1. What is that equal to? Well, we know it's equal to 10 because if we get rid of the ones, it's just equal to 10 times 10, which is equal to 100. But it's also equal to 10. Well, it's equal to 100, which is equal to 10 squared because we know that 100 is 10 squared. Let's do another one. Let's do 10 squared times 10 squared. Let's see what that equals to. Well, 10 squared is 10 times 10. So 10 times 10 times, I'm going to put that in parentheses just to keep us focused here on what I'm doing here. So that's that first 10 squared. The second 10 squared is 10 times 10, which I'm going to move downward and I'm going to say 10 times 10 is 100. And 10 times 10 is 100, which is equal to 10 to the fourth power, or 2, 3, 4. 100 times 100 is 10,000. Okay, or that's equal to 10 to the fourth power. Let's try one more, and then we'll see if we can get a pattern here. Let's do 10 to the third times 10 squared. So what is that equal to? Well, 10 to the third is 10 times 10 times 10. 10 times 10 times 10. And we already said, actually we didn't do it 10 to the third, so that is equal to 1,000, right? Because 10 times 10 is 100. Times 10 more is 1,000. So this whole entire set here is actually worth 1,000. We're going to multiply that 1,000 by 10 times 10, which is, we all know, 100. So this would be 1,000 times 100, which would equal, you add 2 more zeros, because that's how multiplication by tens work. You just add up the zeros. So boom, boom, 1, 2, 3. So we have 100,000, or 10 to the fifth power. So 10 raised to the fifth power. So what we're trying to get is, can we come up with a pattern with this base here, the 10, and these exponents? What kind of pattern can we deduce from what we're looking at right now? So 10 to the 1 times 10 to the 1 ended up being 10 to the 2. Okay, with one example, it's hard to come up with a pattern. But you can probably imagine, okay, well, 1 plus 1 is 2. Maybe that's a pattern. Let's try. Let's go to the next one here. 2 plus 2 is 4, and there's a 4 over here. Okay, so 2 plus 2 is equal to 4. So we have 2 that follow this pattern perfectly fine. Let's try a third one. 10 to the third times 10 to the second. And then we said the answer was 10 to the fifth. 3 plus 2 is equal to 5. You see the pattern? So we're looking at a pattern here. How can we, if we want to write this pattern out, how could we do that algebraically? Because again, I don't know if I'm always going to have a 10. I don't know if I'm always going to have a 3. I'm sloppy with this. Let me change the color here. I don't know if I'll always be using a 10 or a 3 here. It could be a different base and a different exponent, but I want to generalize this. Now, I've only done this with base 10. Maybe this doesn't work with base 2. So, in fact, let's go ahead and do base 2 real quick, some examples. This might really prove our point here. So base 2, if we did 2 raised to the 1 times 2 raised to the 1. What does that equal to? We'll skip some steps here because I think you get the pattern a little bit now. 2 to the 1 is 2 times 2 is 4. So 4 which is also equal to 2 squared, right? So again, 1 plus 1, that's, if we kind of did it out like this, 1 plus 1 equals 2. That's terrible. That's terrible. I think you get the idea. 1 plus 1 equals 2. All right, let's go to another example. Let's do 2 to the third times 2 to the first. What does that equal? Now, we suspect that it's going to equal 2 to the fourth because of our little pattern that we just generated. So, but let's do it out. 2 times 2 times 2, 2 times 2 times 2. That's the 2 to the third. So this is equal to this mess. Ugh, I can't draw straight. Is equal to this mess right here, times another 2 to the 1, which is just plain 2. But if we know our exponents and how they work, we know that if they're all multiplied together, that'd be 2 raised to the, 1, 2, 3, there's 4 of them, so that equals 2 to the fourth power. You could do this out and say 2 times 2 times 2 is 8, times 2 is 16, but 16 is also equal to 2 to the fourth power. So we don't really need to write that out if we understand how this works. So the pattern seems to be following true. 3 plus 1 does equal 4. Looking pretty good. Let's do one more for good measure. So let's do 2 to the fourth times 2 squared. Let's see if that equals 2 to the sixth, which I know it does. And I think you guys get the point as well. 2 times 2 times 2 times 2. That's the first part of this expression, 2 to the fourth, times, and I'll put this one in parentheses. I'll put them both in parentheses. Times 2 times 2, 2 times 2, which again, we have 1, 2, 3, 4, 5, 6 2's. That does in fact equal 2 to the sixth power. So we want to generalize this. Let's pick a different color here. If I told you that we have some base b raised to some exponent, we'll just call it, I don't know, g, right, raised to that power. If I told you that and I said you're going to multiply it by another exponent, b, and now the bases have to be the same. I'm going to tell you that as a truth. You have to prove it and derive it and find examples and patterns like I just did to prove that it does or does not work. But I know that the bases have to be the same in these cases. So b raised to some other letter, f. We don't know what g or f is. We don't even know what b is. But we know that b's are the same. It's two of the same things multiplied. It's not b times c to the f. It's b to the g times b to the f. So the bases have to be the same for this pattern to work. So what does that equal to? Well, we just decided up here, 1 plus 1 equals 2. 3 plus 1 equals 4. 4 plus 2 equals 6. So g plus f equals, well, it equals g plus f. So the best we can do with this expression is call this equal to, and we'll put both the g and the f inside of the exponent. We can even put it in parentheses if we want. So now we have a general equation. So let me rewrite this, g and f. So we have some base b raised to the g plus f. That's what we're saying. So if I told you, hey, what's the answer of 6 raised to the 7th times 6 raised to the 10th power? I can immediately say, oh, the 6 is like the b, right? And g plus f is like the 7 and the 10. So that's equal to 6, which is like the b, raised to the 7 plus 10 power. You could put that in parentheses to, that's a 10, by the way. 7 plus 10, ooh, trial and error. 7 plus 10 in parentheses. Got it? So what does that equal to? My head's almost in the way, but not quite. So is it equal to 6 raised to the 17th power without any of that extra work? We didn't have to do 6 times 6 times 6 times 6 times 6 times 6 17 times to come up with that, right? We did not have to do that. So that's the power of finding these patterns and generating algebraic expressions to represent those patterns. Let's do another one here. Let me erase this right here and move our little, let's move our little guy, our little formula over here. Sorry about my poor writing, guys, but here we are. So one more example, and I think we've got this down. So we'll just do 176 raised to the 13th power. That's probably high. Times, now the base has to be the same for our little example, so it's got to be 176, and raise that to the 35th power. Now doing that out by hand, try doing that. It's ridiculous, right? So it's nothing more than the base, which is the 176 raised to the 13 plus 35th power in parentheses, which is equal to 35 plus 13 is 48. So 176 to the 48th power is the answer. Now that's magical. That's why math is so powerful. Well, I hope you got something out of this. If you did, like and subscribe and share it with your friends, put it on social media, and I will see you guys on the next one.